Let's go ahead and get this on record. So at least that first 22 minutes was not recorded. That'll be okay because I repeat this pretty much the same lesson this evening, and so I'll get it correctly there. Ooh, and I lost my drawing. Rats. Yep, rats. So let's go back to the drawing. Pen, pipe n plus 1 going that way, n minus 1 coming in. So that's what an ordinary junction does. And when the program runs, it'll compute the water depth for some period of time. So let's say it's right here. It's computed this depth indicated by that blue line. Some other features of this drawing that we will keep track of mentally is the bottom elevation is called the invert elevation. Pipe n minus 1 is a certain offset off that bottom. That's called an invert offset. And because of the way this pipe is sloped, this end of the pipe is the outlet end, so it would be called an outlet offset. On pipe n plus 1, this end of the pipe is an inlet, so that's an inlet offset, and it has this value right here. And then pipe n is not offset. So if the offset value is 0, it's just as drawn here. So the pipe bottom and the junction bottom are in the same place. Now in the drawing, obviously the junction has some area, or if you will, some finite volume associated with it. Unless we tell the program otherwise, it will ignore that real fact because it has no other way to do it. And the area, for all practical purposes, is treated as 0. So all it can compute is an elevation, and if it's required to make all the other hydraulics work, that the water come up here, it will report that as the water depth, and then it's going to take this portion and declare it wasted. So it will throw that water away, and it stores it in a loss variable, and that's how we can tell if at this junction our hydraulic grade line is above the land surface. So if flooding occurs, it's only considered when the hydraulic grade line is above the node maximum depth. So in this diagram on the left, the node is not flooded, but as drawn, the pipes would have to be surcharged, meaning that they're completely full. In the diagram on the right, we've drawn it with the node flooded. The pipes are still surcharged, and the flooding is shown up here in the street. And unless we, again, are clever, we can't keep track of that flooding other than to know that flooding has occurred. But if we design a node instead of being a junction node to be a storage node, we actually can enter depth storage tables that allow us to keep track of the volume and storage in this cylindrical part and the volume of storage that's stored up here on the street surface. And that all of a sudden gives us the ability to keep track of what flow depths are on the street surface. And that has some utility in engineering design. So the flooded node attributes, and these are attributes for an ordinary junction node where the flooding feature is turned on, are how deep is the flooding allowed, which is the surcharge depth above the top of the node, and what is the ponded area during surcharge. So essentially what it does is it will treat a node under those conditions as a vertical wall storage tank, as depicted here on the drawing. So when the hydraulics requires that the water be stored at that node, if the storage property is turned on, it computationally pretends there's this tank here, and the tank has a starting value at max depth, and then we give it a ponded area and a ponded depth, and it will store water as much or as little as it needs to meet the continuity requirements. Additionally, in the diagram, we have the invert elevation at the bottom, and here we have an exit pipe and an entrance pipe, and the entrance one is offset relative to the exit. So first, let's apply the SWMM model to a rectangular channel. So no junction nodes, no storage. We've done this problem already several meetings ago in a computer spreadsheet, and all we're going to do is repeat the activity in SWMM. So let me go ahead and get my version of SWMM up and running, and make sure I do not have a local copy. I don't think I do. Okay, so command line interface. Obviously, it will be easier for me if I can find a local copy, but it's actually not necessary, and I think it's probably better that I can't. Okay, that is 5.101, so that's an old version. And that is just source code, no graphical interface. Okay, cool. So I do not have a copy local. I will then use the remote control version for the course. So let me go to SWMM in a box and see if I have the credentials. I don't even know if this is running today. About to find out. Cool. See if I can get it to use up more of the screen. All right, so here's our SWMM in a box. The credential I used was VNC hashtag TWO. So that gets me into this desktop. And let's see what's already there. So there are no graphics. And I'm looking at the file, the input file, just so I can Horton depth. Okay, that's not this particular example problem. So we will go ahead and create our own. We'll do it sort of from scratch, but the one thing we're going to need is, actually we're going to do it without a BMP over underlay. We don't need that. So we're going to represent a rectangular channel. We have most of the hydraulic data required here on the right. Kind of position it there. It looks like it can still see it. So to launch SWMM, we click on the launch SWMM diddler here and wait. And there's the SWMM interface. So it looks an awful lot like the EPANet interface, which is not a surprise because one of the two SWMM programmers actually wrote EPANet. And it looks like I have SWMM 5.1 installed, which is not the latest version. There's the older interface essentially works the same. This will be sufficient for today's lesson. So let's look at the tour of the interface. We have the menu bar at the top. So File, Edit, View, Project. Somewhat similar to EPANet, we can set some project defaults. And what I'm going to do is set my nodes and links to have a conduit length of 200 units to be consistent with the 200 meters here. We want this to be a rectangular conduit, so I'll pick the rectangle. And the bottom width is going to be 1 meter. Let's give it a decent height. Press the okie dokie button. And the conduit roughness is 0.025. Let's get our flow units into either cubic meters per second, which is given to us as an option. We're going to route with dynamic wave routing. And I don't care about the force main. Node invert. I think that will get us through this example just fine. So I'll let that linger on the screen for a little bit so the recorder can pick it up. And now we have the drawing canvas ready to go. So flow units in cubic meters per second. Offsets are set as depth offsets. Let's see what the options are. There's also elevation offsets. Auto length is turned off. That's an advanced feature to try to georeference what you draw. And we've set it up as a rectangular channel, and now we need to draw it. So now we're seagulls. And so we're going to draw this in plan view. So let's look at our sketch. We have something at x equals 0, which is the weir, and then we're moving upstream. So in SWM, the one item we're going to need is we're going to need an outfall, which is this upside down triangle. So I'll select the upside down triangle, and I will draw it on my drawing canvas, and I'm just putting it there willy-nilly. Now I have some knowledge of what this is supposed to look like. And now I want to go ahead and generate a sequence of junctions that are eventually going to be upstream of that point. So I'm going to have flow going from left to right. And all this is a drawing. So if I run out of physical real estate, there's no reason why I can't fold it back on itself. And I'm going to go overboard with the folding just to illustrate that you can. So let's say that that's our system, and then I'm going to join it with conduits. So we'll take this first conduit, and we can go from downstream to upstream, which is usually my personal preference. But just to be different, I'll go from upstream to downstream. And so like in EPANet, I am simply practicing my computer game drawing skills and drawing pictures. Also like EPANet, until I provide the input, the computer program has no idea what these objects are. And the drawing is the second most tedious part of input, the most tedious being to parameterize each of the objects, which I'm beginning to regret that I picked this many, but that's my fault. We'll go slow enough so that the video can capture it, and this should be easy to follow after the fact. Okay, so there's our layout, and what we're going to do is we're going to put flow at this end. So let me go ahead and use the text deal. Oh, that's not a good sound. There we go. So we're able to use our annotation like that. So there's our inflow, and we'll go ahead and we'll have to provide information for that. So in our particular example, the inflow is 2.5 cubic meters per second. So we'll apply it at this location, this junction 20. And in the inflow category, we'll choose yes. And the value we will put is 2.5. You can read the owner's manual on what these other input values are. Choose the okie dokie button, and we've now supplied inflow at that location. While we're here, one of the other things we have to do is supply the invert elevation, because 0 doesn't make sense. We're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 200 meter long lengths upstream of our outfall. So 19 times 200 is a certain number. That's 3,800. And our slope is given as 0.01. So 3,800 times 0.01 should be, that's 1 part in 1,000, so that'd be 3.8 parts. So this should be elevation 3.8. So we would go ahead and tell it that it's 3.8. So the second most nuisance thing about SWM that I think you'll find is it never uses slope as an input. So we actually provide elevations and it will compute slope, which from an engineering design and operational standpoint actually makes sense. But apparently the hydraulic authors 40 or 50 years ago never got the memo from the future. So everything in our textbooks is based on slopes. So we're going to lose 0.2 of a meter every location. So this will be 3.6. And I hope I'm doing this right, and I'll know in a little bit. I'm going to be really mad if I come out off by 1 and have to go to a negative elevation. 2.86 is 2.4. I'm not going to go change it. I will adjust the downstream M to 0.0. We'll just have a really big downstream pool. So we've now set the elevations of everything, and I think the profile grapher will actually work. So we can graph it right now and see if it looks correct. So I have something going on here at between node 8 and 7 that doesn't look right. Otherwise, everything's quite happy. So let's go and find that node and make the necessary change. It looks like I dropped it's perfectly located where I can't do it and get out of the way. It's node 8 and 7. .4 right there. 1.2. 1.0. Oh, good. Turns out that new math I did in my head was correct. I just have a data entry error. 0.8. 0.6. 0.4. Hooray! And this will be 0.2. The other two. There we go. So now I want to try to find that profile drawing. It should be hidden here in the background. I'm going to use this little recycly dealy here to update the drawing. And now I have my channel sloped correctly. I think I'll just leave this in the background. So we've provided input flow. Let's go ahead and verify that the conduits are correctly represented. They are rectangular, 200 meters long, correct. And the roughness looks a little bit too small. We'll have to go fix that. If the roughness is incorrect, it looks like it picked up the other features correctly. So one thing we could do is go through and change them one at a time, but this does provide a group editing feature. So I'm going to surround everything I want to edit with the little marching ant line here. And when I get back, I right click to close the polygon. I do it again. Good, I think it closed it. And then we choose group edit. And I want to edit the property, conduit property. So we choose conduit. The property I want to edit is rougeness. I want to replace it with 0.025. Press the okie dokie. And it tells that 19 conduits were changed. We're happy campers. We'll exit group edit. And we've made the change. Let's go look at our outfall. So currently our outfall is set to a free willy type. And in this case, we're going to, well, we'll leave it be. So a free outfall means that there's nothing restricting the flow going out. So you can think of it as a drop off over the edge of a cliff. So in the vicinity of a free outfall, the flow depth would be whatever the critical depth is. I'm going to go ahead and change to a fixed outfall condition because our particular problem, we are fixed at a depth of 2 meters. And so we will go ahead and provide the depth of 2 meters as the fixed stage. And I believe we're ready to go. We have one other thing to change. We go to options. We'll bring up general. Usually everything's his fault. We'll go ahead and allow ponding for the time being, but nothing should happen. It's default to today's date, and it's going to run for 6 hours of simulation time, which should be plenty. So that's fine. Time steps, we'll leave the defaults in for now, but if there becomes a need to want to change it, we can. It's going to report results every 5 minutes. And our dynamic wave, we have to decide if we want to keep, dampen, or ignore the inertial terms. We'll go ahead and just use dampen because we're after a steady flow solution. And then our surcharge method is Priestman slot or external transport method. Again, we'll keep all the flow in our ditch, so this choice will have no effect. And it has some variable time stepping capabilities, which if you take the open channel flow class or other advanced hydraulic classes, you'll learn what that is from a numerical method standpoint. Essentially what it does is the solution's not changing at some point in time. You can take much bigger time steps without introducing truncation errors. You would have had that in your intro to engineering programming class. We have no files we're going to use. So I believe I have this all set up. Time steps is okay. Dates are set. General is set. Choose the okie dokie button. And now we can go ahead and attempt to run the program. If I've made a data entry mistake that the program can detect, it won't complete the run. It will issue me a warning message. In this case, it says our run was successful. So let's go take a look at that profile, because that's the whole point of doing this. So there's my profile plot, and I look at that, and that is a weird looking water surface profile. Because we have 2 meters of water on the right side, which makes sense, that's our outfall condition. But we have water on the left side, but there's nothing in between. Well, that's because we're looking for a steady flow solution, but what we actually have is a time varying model. So we have to go to a different moment in time. So what this represents is an initial guess of what the water surface would look like after 15 minutes of computation time, assuming at the upstream end we're pouring water in, and at the downstream end we have just suddenly raised a pool. So the first result is meaningless. We let another 15 minutes elapse, and the two water surfaces are joining. And we run all the way out to hour 6. Pretty sure that we're now in steady flow conditions, and that is what the SWMM representation is of the water surface profile. And if we were to compare that to our spreadsheet-based solution over the same distance range, we'd find that the solutions look quite similar. It's essentially doing the same thing. So now we have simulated, hopefully I can shrink that somehow. Oh, I forget how to do that. That's going to be really annoying if I can't make that get small again. Profile plot. Ah, cool. Okay. So now we're back to our study area map. So that was our first example. And now let's use it as a useful tool. Let's see what happens if the flow rate changes. So that was 2.5 cubic meters per second. What if it's 1/10 of the flow? So if we were doing this in a spreadsheet, we would be cutting and pasting something fierce right now. I've just changed the flow rate, rerun the model, press the okie dokie button, bring up the profile, go through the map, and that's what our profile looks like for a much lower flow rate. And then we would ask ourselves, does that make sense? And the answer is yeah. So the water's coming down here, and because we have a 2-meter deep pool, it doesn't start to pile up and form the storage wedge until it gets pretty close to the outfall. So that was our first example, simply a rectangular channel. The reason these are so tall is because we specified a channel depth of 10 meters. Let's go and change that really right now, and then we'll move on to the next example. So if instead of our channel being 10 meters with sidewalls, let's suppose it's something more realistic. Let's say we make it a 2-meter tall channel. Conduit. Hopefully it has max depth. It does. So I'll make it 2.2 meters. I want to try to keep the water in the channel, and then we'll change the flow rate and visualize what happens when that happens. So now we've changed it to a 2.2 meter deep channel. We can rerun the simulation, look at our output, and you'll see that in this instance, all the water is contained in the channel as we expected. But now we can ask the what if question, well, how much flow can this channel accommodate before the hydraulic grade line, which is the water surface, would attempt to leave the channel? And I have a hydraulic cat here. Come on, Atomic Kitty, move your tuchus. Oh, you're not going to move, are you? Yes, I know that my purpose in life is to provide you with food products and such. So let's suppose that we go up to 1 cubic meter per second of flow. So we've done that, rerun. And if you, dude, you got to get off the mouse. That's good. Nope, that foot goes up. Up, good. Wait, you can, there you go. All right. So it looks like I can move the mouse now. You're still going to stay in the way, aren't you? So we've changed it to 1. We'll rerun it. Choose OK. Bring up the profile plot. Go out to our 6 hour, and we can keep 1 cubic meter per second in this channel. Let's go ahead and explore the case where there's 2. Ooh, but you don't want to do that. I just exited the program without saving it, which is perfect. So what we would do is we'd increase that until the water leaves the system. We'll do that in the next one because I don't want to attempt to. I don't think I did a save. Oh, there it is. Oh, please don't be broken. Ah, sweet. Okay, all I did was minimize it. That's close. There we go. If we click on the right thing, it works better. Isn't that funny? So now let's go ahead and apply the two. Choose OK. Rerun. Bring up the profile. and this is actually what I wanted to have happen. What we're visualizing here is at about junction number 10, the water has essentially cannot stay in the channel anymore. So from a drainage engineering perspective, either that channel is not big enough or we're generating too much flow rate. But other than being a visual thing for representing to our clients, that's not entirely useful yet, but we have the report. And if we do the, I think it's the summary report, it will tell us what the depth is at different locations. And so it has the average depth and the maximum depth, and it's telling us that node 22, flooding, node 33, flooding, node 44, flooding, node 55, flooding, and so on. And we can actually sort it, and I'm not sure why the naming convention is coming up buggered up, but that's classic graphical user interface software failures. Even commercial ones do that. So we can actually quantify the amount of the summary. Let's see what a status report is. This is one I was actually looking for. So the status report usually issues a simple warning if flow routing is allowed, ponding is allowed, and it will tell us that we've lost 9.2 million liters of water that it can't account for, because that's the water that left in order for the hydraulic balance at those nodes. So that flooding portion produces a computed estimate of 9 million liters. So that number itself is actually meaningless, but when these are non-zero, when you see the words where the report has a non-zero flooding loss, and you're expecting to contain everything in your drainage network, the program has given you evidence that your design is insufficient. And then you would use that profile plot like I was showing you to attempt to locate where that's occurring and then make necessary design corrections, rerun the hydraulics, and we're all happy campers. So let's go ahead and do the next example, which is almost the same, but the only difference is it's the same, but it's different. A 3 mile long, 60-inch reinforced concrete pipe sewer at 50 milliliter genuine drafts per day. And what's the flow depth if the sewer is on a 1% slope and the downstream boundary condition is normal depth? So this one, we have all sorts of good instructions. Circular, steady, bottom slope, Manning's End. We're told a particular delta X. We're told to use 6 links, and we'll set the boundary. So let me go ahead and save this. And that is Hydro 2, my documents. That's not the right place. I'll save it in a directory called SWM2. And this was lesson 18. Okay, now that that's established, that'll be findable later on. We can go ahead and create a whole new project. Press that. We'll bring the study area map to full size, I wish. Oh, my network lag is horrible today. And we will essentially do the same kind of project. So I'm going to let you all talk me through this. What would be the, based on what I just did, what would be the first thing that we have to address? You can use the chat box if you're afraid to speak out loud. And it's project defaults. Excellent. Good. So we'll go to project defaults. And namely, we're going to mess with the length. So there's going to be 2640. And we're going to set the Manning's N of 0.015. And we're no longer rectangular open. We want to go to circulated. And actually, I want to get the diameter correct. I'm going to use a 60-inch pipe. And dimensions are meters unless otherwise stated. Okay, so I think 60 inches, 5 feet. And we're still in SI units. We will change it to using million gallons per day. So now let's see if it picked up that change or if I actually have to save the, there we go. So 5 feet diameter. So it uses a kind of a weird nomenclature for things like pipes that only have one characteristic dimension. That characteristic dimension is called the maximum height of the object. For other things like rectangles, which have two characteristic dimensions, which is its width and its height, then there'll be a width and height and so forth. The irregular one, we'll get to that in a future class because that's how we represent street sections and natural streams. So we'll choose OK. And I think that is good. We'll make other changes as we proceed. Okay, so somebody other than Elizabeth, next question. What will we do next? So we've set the project defaults. We want to locate a particularly special node. What's that special node called? The outfall. Excellent. So where I put it doesn't matter. Rather than being a smart aleck and trying to have you tell me where to put it, I'll just it's weird. Click on the map where the node should be placed. Okay, we're happy? Finally, we got a node. I don't know why it ended up down there. That's that network lag again. So now we've made the outfall. It says we're going to use 6 links. So if we have 6 links, each link has to have a node at each end. What's our total node count going to be? We can include the outfall nodes. So I believe we're going to need 7 nodes. So that gives us link 1. Link 2. So we're waiting on network right now because I already clicked it. There we go. 1, 2, 3, 4, 5, 6. So let's count our nodes because we think it's 7. So there's 1 node, 2 node, 3 node, 4 node, 5 nodes, 6 nodes, 7 nodes. Boy, we are actually good. We're really good. I mean, I know that. So now we have to, before we connect everything, let's go ahead and set the node elevation because I find that a monumental pain in the neck. Each node is 2,640 feet apart. It's on a 0.1% slope, which is 1 part in 1,000. So each node is 2.6 feet different in elevation. So if the outfall is declared to be 0, the first node is going to be 2.6 feet. So we'll go ahead and put its invert elevation, 2.6. Now it's going to be the fun part because I'm going to have to do simple arithmetic in my head, and I will start to fail at that. So 2.6 twice is 5.2 plus 2.6 is going to be 7.2, 7.8. And who said that stuff we learned in first grade wouldn't be useful? 7.8 plus 2.6 is going to be 7, 8, 9.8, 10.4. We'll go ahead and plot a profile and tidy things up if I've screwed up too badly. 10.4 plus 2.6 will be 11, will be 12. And finally 14.6. So as I said earlier, this is the most tedious part of this interface, is setting elevations. So if we have a case where we have hundreds of nodes and links, we want to set the elevations fairly systematically. At something of that scale, it's sometimes actually easier to go into a text editor and directly edit the input file. So we've now set elevations. The next thing we can do is we will connect nodes with their links. We've already designed the links, so in this particular case, they all have the same geometric properties, so all we have to do is draw them. And I'm drawing from upstream to downstream. That's a matter of personal choice. But I will show you where it matters in a second. So there's our system drawn. Again, we are in plan view. We have two things left. So we got the slope, we've got Manning's and we got delta x. We need to set the outfall boundary. We need to put the inflow. Let's go ahead and turn some things on. Let's make those a little bit bigger. Actually, I think you can see them. So again, in the tools, map display options, tools, map display option. Going to try to make things a little bit larger. There, I think you can see it. So the numbers that are next to the nodes are the node ID. The numbers that are next to the links are the link ID. So for example, this one is junction 8. This one here is junction 4. And some of them are out of numerical sequence. That's fine. The net effect of that is it's just changing the structure of the node incidence matrix, but the solver can keep track of that. So my next question is, we have to apply 50 million gallons a day to this system somewhere. Where should we apply that? Node 7, node 6, node 5, node 3, node 4, node 2, or node 8? Node 8. Excellent. Yeah, there'd be no point in building this entire system if we're not going to use the upstream portions. And so now we give it a baseline flow of 50. And then the last thing is we want to set the outfall conditions. We're told in our problem statement that it's a normal outfall. So what normal means is it's going to compute the slope from this upstream conduit, and then it's going to use that slope in a Manning's equation to figure out what the outfall depth would have to be for 50 million gallons per day. Let's go ahead and quickly generate a profile plot before we attempt to run it. So start at node 8. I'll end at the outfall. I will let the computer program traverse the network and find the best path. I'll press the okie dokie. And there's my profile, and it looks like I have made a mistake on node 7 in terms of its elevation. So let's go ahead and try to fix that. Node 6 is 10.4, and I want to add 2.6. So 10.4 plus 2.6 is 13. All right, yeah, 2, 10, 11, 12. So we check that, and then I'm going to have to adjust node 8. So 13 plus 2.6 is 15.6. Redraw it, and that looks like how I intended it to look. Okay, so now we're ready to attempt to run our program. Let's slide this out of the way. It's not accepting input now. Come on, AT&T, push those bits through the wire. You can do it. I'll see if I get the run command sent. So there's our simulation, and by looking at it, it looks to me like that pipe is beyond full. So what did you click to open the profile again? I clicked on the little picture of the profile. Or I think it's in tools. Nope. View. It's in one of these things, but there's the profile tool. Okay, so I would say that the picture suggests to me that our pipe is too full. How would we check that? What thing did I show in the previous example that we used to quantify whether or not all the water was contained in the drainage structure? Anybody remember? was in report, and we will do the status report. Right here we have a computed flooding loss. And given that our flow units are 50 million gallons per day, if we've lost 600,000 gallons during the 6-hour simulation, we did not contain all of our flow in our drainage network. So either we need to reduce the flow rate, make the pipes bigger, or make the pipes smoother. I'm going to reduce the flow rate, because making a pipe smoother, we can only do that on a piece of paper. In real life, we're kind of stuck with what the material gives us. Making the pipes bigger after we've put them in the ground is an expensive proposition. Let's try 40 million gallons per day. So 20% lower flow. I'm trying to go from memory. I think this will actually work. So our pipe can easily accommodate 40 million gallons per day, and it starts to fail at 50. And then by some trial and error, we can simply change these values. Actually, there's another way to do it, but we'll do it the tedious trial and error way. We can change these until we just contain the flow in the pipe, and that gives us a good assessment of what the capacity of that pipe is, based on the hydraulics that is modeled for us in the SWMM hydraulic model. I think that one's going to be just fine too. Nope, I filled it up so it can't accommodate 48. Hard to believe how 1 million gallons per day can make a difference. It's either 47 or 46 fits in this pipe. So the pipe is still filling up. If we ran this longer, we would lose capacity at the upstream end. So I guess my memory of 46 was the best one. And in essence, we're doing iterative design. So that's just catching the top of the pipe at the downstream end. It may not even be able to accommodate 46 million gallons per day, but somewhere between 45 and 46 would be a good design flow for this particular system, because all the water is contained in the pipe. And we'll look at ways to accommodate water being stored on the surface in a different meeting, because we're almost done with today. Okay, so 45 fits easy. That extra million gallons per day starts to challenge our system. And that would be how we would use the hydraulic program to help us evaluate our design. So it's going to make me do this every single time. Every time. So now I'll exit the program and I will finish up with the parts of the PowerPoint. So what we'll do next meeting is we'll actually drop the Goodwin Street example into SWM. So we have done this example and that example, mostly as the introduction to the program. And I think you can see from the examples that it's not that difficult to make an initial design and parameterize it. The challenge comes when there's a lot of nodes to deal with. So our next one is going to be this problem, which we have already examined. And we've done most of the preparatory information. We're going to need this sheet, and we're going to need the bitmap graphic. So it's 12:24. So I am actually 4 minutes over. So lesson 19, we will pick up. We'll pick up right here, and we will start to build this example in our SWM program. And that will come in handy for when you're going to do your Somewhere USA drainage design. Because we're going to do this again for our study watershed that was invented for this class. So if there are no further questions, so has the previous video been uploaded? I'm pretty sure it has. Let's go to YouTube and check that out. Lesson 17, which was Tuesday's lesson, has been uploaded a day ago, and I can't seem to find section 2. That's weird. Pretty sure I did both sections. It's definitely not here in the list. So the lesson 17 from on Tuesday for the morning section, which is your section, is not uploaded, but lesson 17 for the evening section is uploaded, and the topical coverage was about the same. So if you're in a hurry, Cole, you can go to the YouTube and find this this link. It's turned into public because it's just been easier to make it searchable. So you should be able to search for, actually I'll drop the link right into the chat box. That's probably faster for everybody. God, I hope this doesn't break Zoom. So that that video will get you started, and I'll get started on uploading our video. I seem to recall that last Tuesday I was having difficulties with the video, so I may have actually lost the video stream, and that's why there's nothing there, but I'll check that.